Part 2 of Lesson 3.2 is going to be on analyzing the graphs of logarithm functions. Part 1 was on evaluating expressions involving logarithms. So the first step is to understand what the graph of a logarithmic function looks like. And if you take a look right here, this is the graph of an exponential growth function. And then if you look at this one, this is the graph of a logarithmic function. Now, one of the things for you to understand is that those two functions, an exponential function and a logarithmic function, are inverses of each other, which is why you see the diagonal red dashed line, because the relationship between a function and its inverse is a diagonal reflection about the line y equals x. So that's what a logarithmic function looks like, logarithmic graph looks like. Yesterday we talked about common logs. Common logs are logs that look like this, and there's no base written underneath it. And so when there's no base written underneath it, we assume that there's a 10 there, and we call that a common log. So the graph of a common log is this one right here. This black graph increases pretty fast. And then, sorry, that's an exponential graph. That's not the log graph. That's 10 to the x. And then the common log is its inverse, which is right here. So that's the graph of a common log. We also talked about a natural log. And a natural log is when we have the letters ln, and there's no base written for this as well, and so the base of e is assumed to be there. Remember, e is a number approximately equal to 2.718. You got introduced to that in Algebra 2. And so if we look at the graphs, we first have the graph of just e to the x as an exponential growth function. And then if you look at its inverse, which is the natural log of x, it looks something like that. So all of these graphs look very, very similar to each other. So here's the kind of examples you're going to have. It's going to say sketch and analyze the graph of each function. Describe its domain, range, intercepts, asymptotes, end behavior, and where the function's increasing or decreasing. Well, the first thing I want you to understand is that what we're looking at is the log of x base 3. And this is in logarithmic form. We could change it into exponential by saying 3 to the y equals x. This and this have the same meaning. Okay? So let's make an xy table. And let's come up with some coordinate points that are going to be on this graph. Okay? So let's go with y equals 1, then x would equal 3. If y equals 2, x would equal 9. If y equals 3, x would equal 27. Okay, so those are some coordinate points for this logarithmic graph. Probably should have started with this one. A good one to start with is y equals 1. Y equals 3. 3 to the 0 equals 1, so it's going to pass through those coordinate points. So from that xy table, we can produce this graph right here. You can see this is the log of x base 3. Its inverse is also graphed here at the same time, which is 3 to the x. And it passes through the coordinate points that we came up with right here on the previous page. It goes through 1, 0, 3, 1, 9, 2, and you can see those coordinate points plotted right here. Here's 9, 2. Here's 3, 1. Here's 1, 0. And there's additional points that you could plot there to get that graph. So if you look at all the specifics, the domain is from 0 to infinity. That graph completely stays to the right side of the y-axis. The range is all real numbers. It keeps going down forever and it keeps climbing up forever. There is an x-intercept at 1. There is an asymptote. It's a vertical asymptote. It's the y-axis, which could also be written x equals 0. End behavior, as you go really far to the right, it keeps increasing right here. Now, it doesn't keep going really far to the left. That's why you can see right here on the end behavior, they say as you approach 0 on the right, it goes down. Okay, we'll talk more about that in class. And then this function's an increasing function. It never goes down as you move left to right. So here's the same kind of problem, but what's different about this is your base is a fraction less than 1. So let me first change from function notation into an equation. And then let's change it from logarithmic form into exponential. 1/2 to the y equals x. Then let's make an xy table. Okay. Now, one of the things that we'll start with is a y value. Let's start with a couple of negative values here. Let's go -2, -1, 0, 1, and 2. Let's start with the easy ones, right? Let's start with y equals 0. 1/2 to the 0 is 1. Another easy one. 1/2 to the first power is just 1/2. 1/2 to the second power is 1/4. Now going into the negatives here, if you have 1/2 to the -1, negative exponent reciprocates, so that gives you 2. In the same way, 1/2 to the -2 is going to give you +4. So if we took these coordinate points and graphed them, we would end up getting a graph that looks something like this. Okay, slightly different graph. All the specifics are listed over here on the side: the domain, range, intercepts, asymptotes, end behavior, and this would be a decreasing function. But this leads us into talking about logarithmic growth versus logarithmic decay. Just like exponential growth and exponential decay, there are logarithmic growth graphs and logarithmic decay graphs. And as you can imagine, a log graph, like you can see here, moves up and to the right. Okay, a logarithmic decay graph moves down and to the right, as you can see here. All the specifics of these are listed down below: domain, range, intercepts, asymptotes, extrema, which are mins and maxes, and end behavior and continuity. So that's something to take note of. And so the last kind of problems that we're going to discuss are right here. Example 6. Use the graph of this function to describe the transformations that result in each function. Then sketch the graphs of each function. So we're going to compare this, just a basic common log graph, log of x base 10, into part A, part B, and part C. Well, on part A, we got this +4. And you have to ask yourself, is the +4 inside or outside? And you can tell that it's inside, and so our rules are it's going to affect it horizontally. So we say it's a horizontal shift to the left 4. Remember, anything inside behaves illogically. On part B, we've got two things. We've got the -5, we've got a negative sign out in front. You've got to ask yourself, is that -5 inside or outside? It is outside. If it was inside, there'd be parentheses like we had in part A. So we got to shift down 5. And then that negative sign in front of the log of x is going to be a reflection. That also is outside, therefore it's a vertical reflection about the x-axis. And then part C, we got two things happening. We got the +2, which is inside, and we got the times by 3, which is outside. So we have a shift to the left of 2, then we have a vertical stretch of 3. So there's your transformation. Same kind of rules that we've had with exponentials and other types of functions. Here's sketches of each of these. If you take a look at on part A, the blue graph is just the common log of x, and if we move that to the left 4, you'd get the red graph. On part B, the blue graph is just the common log of x, and if you take that and reflect it vertically about the x-axis, and then move it down 5, you'd get the red graph. And then on part C, you've got the blue graph is just the common log of x, and if you move that to the left 2 and then vertically stretch it by a factor of 3, you'd get the red graph. So this is exposure to the graphs of log functions and also discussing transformations on log functions. Here's the homework problems to be working on, and this will be collected on Monday. Also a reminder, there is a quiz on Monday on lessons 3.1 and 3.2.